Okay. Any questions before we get rolling today? Don't forget, I will not be in the office Friday. I will actually be out of town. I hope to be back to the math club, which, by the way, you should really consider coming to. We have a graduate student talking. She's fantastic. And she's going to talk about cryptography and some of the history of it. Some of the stuff that was actually discovered and was classified until like 1997, which is kind of cool. Don't forget the math in Saturday. You will have class on Friday. I've got a so that's plan. So the math in will actually take place in this building where you go to the appropriate. I'm gonna put signs up, don't worry about that. And the candy's gonna be full because there's banana ball and you can't do this banana ball, but there will also be the math in, which is fun. The math club will be Friday, and I will be around for office hours during files regular time and probably more. So if you need to talk to me before, and we've also got review. Tuesday, 429. In we couldn't actually get this classroom because it turns out there is an exam here, but I got us a room upstairs, Martin's 307. So Tuesday at 6. Take advantage of your resources. I will be around Monday and Wednesday. Next week, probably Tuesday too, but email me if you need anything. So last time we showed that if you're compact, you're closed and bounded. And the way we did this was sort of contrapositive. We assumed that the set is not closed, showed it could be compact. We should assumed it was not bounded, showed that it couldn't be compact. So let's finish this by looking at the other thing. So I left you actually, we went only into the other arrows so far, so far enough for me to find the following sets. Suppose C is closed and bounded. And suppose the script C is an open cover. Two loops on it, so you can say open cover and C. And so what I have is regular C is a closed and bounded set. Little funny fancy C there is an open cover. So this is a bunch of open blankets that cover up C. We have to show that we can cover C with only finite many out of it. So we need to show C is covered by a finite subset. And what I left you with to consider was this. Here's my notation. So for this proof, I'm going to call this important subsets of R. Number one, for all X in R, C sub X is a set of A and C such that A is less than or equal to X. So imagine that C is some set. It's a closed and bounded set that's spread across the real line. This is sort of like a little So if C looks something like this, it's close enough. C looks something like this, and X is here, then CX is everything in C, right? If X is here, then CX is everything in C that's to the left of X, including X, right? So that's all that is. This is just like a measuring stick that I can move back and forth. Notice that since C is a bounded set, if I move X far enough away, then CX is all to C, right? Because everything will, if I move this far enough to the right, everything will be to the left of it. And by the same token, if I move this far enough to the left, it'll eventually be empty, right? Because all the stuff to the left, since this is bounded, it's got a floor. So if I move this all the way over here, there'll be nothing left to the left of it. Everybody okay with it? And another set that I define in this proof is D. This is the set of X and R such that CX is covered by finitely many elements of the covers. So D is everything in R that it's everything in R since CX is covered by finitely many things in C. Let me point out that for example, if your X is all the way to the left of C, that means that CX is empty, and that would be covered by finitely many things, right? So D is not empty. In fact, everything to the left of the set C has this property. Because if you're left of the C, then CX is the empty set, and that's something covered by finitely. Everybody okay? I know this can be a little hard to figure. Okay. So since C is bounded, one of our assumptions about it, if C exists and is in C, since C is also closed. The infimum exists because C is a bounded set, and bonus, since C is a closed set, that infimum has to be contained within C. So, and I kind of explained this to you a moment ago. So if X is less than MC, then CX is the empty set, because if I move X far enough to the left, there's nothing left in C to the left of it. And so X is in D. So D is not an empty set, as I pointed out earlier. Now, D has no upper limit. So no matter how far, no matter how far I go to the right, there's always going to be something in D that's even further to the right. So that's what I mean by it has no upper bound. Let's try to prove that this is true. Suppose, by way of contradiction, that D does have an upper bound. Does have an upper bound. And so it's got a supremum in that case. So if it's got an upper bound, then it's got a supremum. Supremum is the least upper bound. That's an element of R. Now, let delta be 0, let delta be bigger than 0. And choose B and B such that S is the supremum of set D. So no matter how small delta is, there has to be another D in between here. Otherwise, S wouldn't be the least upper bound. Because if you could ever find delta so small that there's not a D between there, you can lower the lower bound. Everybody okay with that? So no matter how small delta is, bigger than 0, there's some D and D that I can squeeze in between S and S minus delta. Now, if the neighborhood about S with delta intersect C is empty, that is to say, this is the neighborhood of length delta around S. If there's nothing in C here, no, there is this D, but suppose there's nothing from C there, right? The original C, then CD, let me call things. Is equal to such that C is less than or equal to S plus delta over 2. All this is saying is if you can't find anything from C in between these two numbers, then all the stuff in C that is less than D is the same thing that's all the stuff in C that's less than S plus delta over 2. Right, because delta over 2, that just goes in this width right here, and there's nothing in C there, right? So really we're saying since there's nothing in C here, everything in C that's to the left of D is also everything that's to the left of S plus delta over 2, right? There can't be anything else in C, right? And this is going to give us a contradiction because right, because this as D is in D, and so notice that S plus right? Because I can cover D with it, right? Since D is in D, I can cover everything in here less than D with finitely many sets. And now I just need this other set here to cover, to also get this other point here. So, in other words, this contradicts the fact that S is the supreme of D. Because this thing that's a little bit bigger than S is also in D, right? So it's certainly, S can be the supreme because there's something in D that's a little bit bigger. Because we can use this one extra open set to get that. And so this is also covered by a finite number of sets. Okay, any questions? So what conclusion do we come from can we get from this? So what we can get from this is for all delta bigger than zero, C intersect S delta is not it. That's what we conclude from what we got here. So as C is closed, we proved this last time. If you have a closed set and for all delta bigger than zero, this neighborhood intersects this. That means that S must be in C. So the supremum of D must be in C because C is closed. Now, let U be in our cover such that S is equal. We know that S is an element of C, right? And we know that fancy C, that's a bunch of blankets. My blankets cover up all of C. So in particular, the point S is covered by one of these blankets, right? This is a point in C, it's got to be covered by some of the blankets. So I'll pick this blanket out. There could be many choices, but I'll let U be one of the blankets that happens to cover the point S. Since U is open, S is an interior. S is in U, so it must be interior point as it is open. So there exists epsilon bigger than zero, such that the neighborhood with epsilon around, a little interval around with epsilon around S is completely contained in U. Now choose D1 and D. Such that S minus epsilon D1 less than S. So choose something else from D that is between S and S minus epsilon. So in other words, D1 and again, since S is the supremum of D, it has to be in there. Or there has to be a D1 that's in there. Since D1 is in D, there exists a finite collection of open sets from cover C, and I'm going to call it something. U1, U1, U2, up to UN, such that CD1 is contained U1, U2, UN, union, U, where U is this little neighborhood that picks up S, and of course D1. Everybody okay so far? Okay. So this is where we show that we can't finally complete this, that D can't have an upper bound. So you know that CD1 this set, because D1 is in D, this has to be contained in a finite union of blankets. And one of these is U, which extends in both directions epsilon from S. So now let Y equal S plus epsilon over 2. Notice that this is still in U, because here's U. This is S plus epsilon. Y is S plus epsilon over 2. So you go from S halfway here. This is Y, and notice it's contained in U. Okay with it? And here's the rub. Note CY is also contained in U1, union U2, union UN. Because we've got all the stuff before U covered. And so all we have to do is vary this Y out here a little bit. And now we have CY is also contained in. But so CY is contained in finitely many open sets from U. I'm sorry, C. So Y is in D. But Y is bigger than S, which is the supreme, which is a contradiction. And so D cannot have an upper bound. Well, let me recall for you because I erased it. Remember what D is? D was the set of, let me use my original notation here. D was the set of X and R such that CX is contained in finite many elements of C. So I really like the punchline of this theorem. We're almost there. But D has no upper bound. Right? That's what we just spent all that time proving. I mean, so no matter, there's always points from the D further to the right, right? Let C equal the supreme of C. Now we do know that C has an upper bound because C is closed and bounded, right? So C has an upper bound, right? Let D and D be such that D is bigger than notice that uh, uh, right. Since D is in D and D is bigger than sup C, CD is equal to C. Right? Because remember, CD is the set of X and R such that X less than X and C, such that X is less than or equal to C. But everything in C is less than or equal to D, right? Because D is greater than the supreme number of C. In other words, everything in D is to the left of little d, right? So this is C. But CD, which equals C, is contained in finitely many open sets from space by definition, right? Because since D is in D, CD is contained in finitely many elements of C. So C is common. CD is all of C, but CD by definition means that, well, in this case, all of C is contained in finite many sets. I think this is fascinating proof because I only use properties of rule. I never actually wrote down what these sets are. No matter what this collection is, you got to be able to put this in finite many, right? But I think this proof not easy, right? You got to think about it quite a bit, and this actually shows that the real line, there's a lot of subtleties. Okay, any questions on that? I want to give you all, I gotta introduce like a couple of technical things before we do Bolzano-Weierstrauss theorem. I'm gonna start this off definition. Let A be a subset of R. So A is some subset. A point in the real numbers is an accumulation point. For A, if for all delta bigger than 0, the neighborhood about X, radius delta, contains at least one point of A that is not X. Let me give you an example. I'll illustrate this. For example, so what it means to be an accumulation point, this point is not necessarily in the set. What it means is no matter how tight of a neighborhood you have around that point, you got to have at least one point from this offending set A is different from your accumulation. So example, let A be the set 1 over n in the natural numbers. So let me kind of draw you this here. Here's 1. Let's see. Put this to be 0, say. So here's what you have in your set. You have 1, you have 1/2, you have 1/3, 1/4, 1/5, 1/6, etc., etc., etc. It's a set, have an accumulation point. You think of any point, no matter how small the neighborhood around there is, you get something in the set that's not the point itself you picked. Yes. Zero is 0 in the set? No. But I could throw 0 into the set and it would still be an accumulation, right? Because no matter how small the neighborhood around 0 you get, there's always at least one point. In fact, not only that, there's infinitely many points in the neighborhood. Everybody okay with that? Is it the only accumulation point? The answer is yes, right? Well, let me ask first this question. Can any of the points in the sets themselves be an accumulation? No. And here's the reason why. If you have a point in the set, it's from 1 over n, and it's got a next neighbor that's in the set that is the closest point. Right. Measure the shortest distance, cut it in half, and that neighborhood around here will contain no other points, right? And if you have, there's a similar argument, if you have any point to the left of 0, all you have to do is just take a neighborhood halfway to 0, and you can't get anything in the set. And if you have anything that's positive, then if it's to the right of 1, there's no neighborhood around it. And if it's something between 0 and 1, all you have to do is do a similar argument because it's between two consecutive 1 over n and 1 over n plus 1. So you can put a little neighborhood. So 0, in fact, is the only accumulation.
Can you see why 0 is the accumulation?
Because if you have 0, the neighborhood about 0 with delta is exactly equal to the interval minus delta to delta. Right? All you have to do is find n at, how about m, such that 1 over m is less than delta. And that'll be a point in the neighborhood, right? And you can always find m big enough such that this is true. That's the Archimedean problem. Right? Is that cleared up?
Yes.
Okay. Definition to follow up this. This is really a notation more than a definition. Given a set A and R, we define A prime to be a set of accumulation points. Notice A prime can certainly be empty, because, for example, you might have A to be a single point, and a single point never has an accumulation point. So A prime, but when you see A prime, that just means, that's a set of accumulation. Proposition 733. A set A in R is closed if and only if it contains its accumulation. This is kind of an interesting way to think about a closed set. Remember, a closed set's a complement of an open set. A set is closed if and only if a set of accumulation points of A is contained in it. So let's prove this. Suppose A is closed. And we'll say that, say X is in A. That is to say, suppose that X is closed and X is just some accumulation point of A. Suppose that X is an accumulation point. Let's suppose that X is not an A and see if we can derive some kind of contradiction from that. Then X is in U, which is R minus A. And what do we know about the status of the set U? It is the complement of A. And so, yes.
Maybe it's bad time to ask, what is that signal?
Which one? This?
The color of the
That means I'm defining it to be equal, right? So it's like giving it a name. So 2 plus 2 equals 4. That's an equation. When you see this, I mean, the set U is defined to be R minus A. Others? What's the status of U? What's that? It's open because A is closed, U is open. And of course, you might be able to tell this is coming. So there exists a delta bigger than 0 such that neighborhood about X, radius delta, is completely contained in U. But now, this neighborhood, U, I'm sorry, in X delta, can contain no element of A. Right? Because this neighborhood is contained in U and all of U is in the complement. So there's no way to put something in the neighborhood of A in here because this is contained in the complement of A. So X cannot be an accumulation. And there is our desired contradiction. So this establishes the first direction. If A is closed, then A prime must be contained in A.
What's the word after this?
Neighborhood.
Oh.
Right, and highly abbreviated neighborhood. Sorry about that. Mr. Rogers would be very angry at me. Now, suppose the set of accumulation points of A are contained in A. It suffices. I'm trying to show that we're trying to show that A is closed, so it suffices to show. Suffices to show that the complement of A is open. If not, if U is not open, then there exists an interior or a point that's not interior. Not interior. So if U is not open, then there's got to be some point it's not an interior point. And what does that mean? Well, so that means that hence no neighborhood of the form in X delta, here delta equals 0, is completely contained in U. So there's always stuff in this neighborhood. For every neighborhood, there's got to be at least one point that's not in U. That is a key neighborhood of X contains a point of A. And this point or points must be different from X. As X is in U, which is a complement. Therefore, X is contained in a complement, which is contained in A, which is our computation. And there we go. Questions? This. Let me give you two more theorems here. Here is the Bolzano-Weierstrauss theorem. Bounded infinite subset of R as an accumulation. This is kind of a big theorem here because it shows certainly you need bounded. You need infinite's not going to be good enough. Can anybody give an example of an infinite subset of the reals that has no accumulation point? What's that? That's a great answer. The natural numbers has no accumulation point. Because notice they're all spread out, right? And you can't get the clumping in the neighborhood you need, right? But that's an infinite set. I have too much room to move around, right? So it's a different story if it's bounded. So now instead of saying, so Sophia cheated on me by spreading her infinite set all the way across reals, which is what you want to do. But if I said, okay, Sophia, Now, give me an infinite set in here. You're bounded and you're infinite. No matter how you try to put infinitely many points in between these, there has to be at least one accumulation point, which might seem intuitively obvious, but maybe not. What if I clump it up for a while here and clump it denser here and clump it denser here and try to move it around so I dodge an accumulation point? This theorem says you can't do that. No matter how you try to dodge it around, as long as as long as it's bounded and infinite, you have to have an accumulation point. Some point where no matter what, any neighborhood contains at least one element set. This is a fascinating result. We're going to prove this in a moment. And here's the follow-up so you can see kind of the end of the line here. Theorem, and this is what I promised you. This is called Bounded Monotone Sequence Theorem. And now you're probably starting to see why they didn't prove this, because you need a lot of background to this if you really want to do it right. Every bounded monotonic sequence this is something that I'm sure that you at least saw mentioned in Calc 2. If you have a sequence that is bounded, so it's got a floor and a ceiling, and it's monotonic, that is, it's always getting bigger, or conversely, always getting smaller, then it has to converge. And I pretty much guarantee they didn't prove that in 1080. They might have done a picture of something to appeal to your intuition, which is pretty good, but to really get in the weeds is difficult. Uh, 735 we'll do next time. Let's prove let's approve this. And perhaps you see why Bolzano-Weierstrauss is necessary, because this says that if you have an infinite set, you have to have an accumulation point. That's essentially going to play the role of the limit in 735. Suppose A is bounded and infinite. And has no accumulation. We're going to try to get a contradiction from this. We're going to assume that's bounded and infinite, yet there is no accumulation point. Hence, A is closed. Because it's bounded and infinite. Wait a minute. Oh, right. It must be closed by the previous theorem, right? Yes. A is closed. And bounded. Yet compact. It's closed because no accumulation points means A prime is the empty set, and the empty set is of course contained in A, so it must be closed. It's closed and bounded, so it's compact. Since A has no accumulation points, for all X and A, there exists deltas of X, such that, well, we have 0, such that the neighborhood about X, delta X, intersect A is only X. Because there's no elements in that set outside of A except for in A except for X itself. Hence, for all y and x different, the neighborhood x delta x intersect the neighborhood y delta y is empty. These sets in x delta x form a cover. Open cover. Because every x is in one of these. And since there exists infinitely many x in A, there exists no phi circle. Contradicting facts. What we've shown is for every point in A, this little neighborhood around it doesn't pick up any other elements of A. So you need exactly all these to cover it, because every point in A is contained in only one blanket. You've got a blanket for every single point with no overlap. Since there's infinitely many points, it's an infinite cover, and you can't pull anything out because everything needs its own blanket. So that contradicts compactness. Any questions on that? Next time we will prove 735, maybe talk a little bit about topology and well, so this is my last formal day in front of you. I hope I see all of you at the math end and during office hours. I've enjoyed having you as a class. Even those of you out there that I know miss me, and I will see you all, well, hopefully Friday afternoon I get back to the math club. If not, hopefully at the math end.